Very important topic in Calc 1 and Calc 2, and now we're going to do it in Calc 3. Wait till you see the second derivative test in Calc 3. This is going to be fun. Okay, so first let's figure out what is a maximum and minimum point. Well, we have to write this down.
I get worried when you use that.
I mean, they're sort of the same definition. Function z equals x. Y has a max point at x naught, y naught if f of x naught, y naught is greater than or equal to f of x, y. Right, so we're looking at things on a disk, right? So
near means disk centered on.
this centered at this.
Okay.
So all points is near, right? So it means on some, well, it should involve center. Why not? It just means if you zoom in close enough, that point is higher than every other point. That's all it's saying, right? Zoom in fast enough, far enough, this is smaller than any other point around the value. Right? You have a smaller z value, which defines the height. So what else do we need to do? So here, again, more familiar terminology. F of x naught, y naught is called a local maximum or minimum. Respectively, if the above holds all points So we're just defining that. Zoom in far enough, this is bigger than every point, it's a maximum. Zoom in far enough, this is smaller than every point, it's a minimum. And they're called local maximums and minimums. And if that happens for all points in some domain, then you call them absolute max or minimums. Sort of the same idea from Calc 1 and 2. It's not anything really different. You're just zooming in. Theorem. Again, something that's not completely surprising. If f has a max at a point respect to x is 0. Partial respect to y is 0. Okay. And we're not going to prove this, but the same proof is the one you'd have done in calc 1 using Vermont's theorem. Basically, you fix one variable and you think of it as a function of x, and you guys, oh, the derivative has to be 0, just like in calc 1. Then if you fix the x and let the y vary, oh, the derivative has to be 0. You sort of put them together and realize your derivative in both directions of x and y have to be 0, right? So that's not surprising. Again, maximum and minimums occur where your derivative is either 0 or, of course, undefined. More terminology. We're about to get to something different, but so far it's sort of... Critical points is where your derivative is 0 or undefined. Here we're using partial derivatives. Again, no surprise there. Let's actually find some points. Trying to find the critical points here and then try to classify them, if we can. So far everything's intuitive. It's just, now instead of using a derivative, we're looking at the partial derivatives, but pretty much the theory all holds true up to this point. So critical points are where the derivative is, but now you need to have both equal to 0. It's not good enough to have one equals 0. It has to be both. Because otherwise your tangent plane wouldn't be flat. That's sort of the whole point. Because a maximum or a minimum, remember, you'd expect the tangent plane to look like z equals a constant, right? But as long as one of these aren't 0, that won't happen. Right? So you can actually justify this using the formula for the tangent plane that we know. These actually give you the coefficient of the first two coordinates of the normal vector. So start with A. How do we find the critical points?
Take the partial, set them in equal 0,
So
and
we
solve.
have fx equals
4x plus 8.
and fy equals,
2y minus 6.
so for, right, these are never undefined, so for critical points, you need 4x plus 8 equals 0, and at the same time, you need 2y minus 6 equals 0. This means the critical points are,
2 and 3.
right, there's actually no, come again?
Yeah, negative 2, sorry. No, 2.
Negative 2.
Negative 2. Yes, negative 2,
Minus
sorry.
8.
So what's the point?
Negative 2 and 3.
Right, there's, it's literally one coordinate, right? You don't think of them as separate points, right? This gives you the x coordinate, it has to be minus 2 to make that 0. The y coordinate has to be 3 to make this 0. So the only place where both of these happen at the same time is that coordinate. Right? So there's only one critical point, so the critical point is, it was hard to see if you guys can think of these things. So there's only one critical point here. Can you classify that? Could you tell me what kind of critical point that is?
You mean whether it's a maximum or.
Maximum or minimum? Right, but then you'd have to test that it's actually bigger or smaller than all points in a region, but there'd be an infinite number of points to check. How can you know?
Second derivatives.
Well, that's a good idea, and we are going to use a second derivative test, except I didn't show you how to do it yet. It's actually not as easy as
Right, because
in top one.
Wouldn't it be according to the direction vector? If the vector, didn't you say that in the last chapter?
Wouldn't I like the direction? Yeah?
Can't you check the partial derivatives when they're equal to 0, when they're positive and when they're negative? Because if the partial derivative at a certain point is positive for both f at that point for fx and fy, that means the function is increasing. If they're both negative,
Nope.
not necessarily.
Yeah, that's where your intuition breaks down. That is not true. You're talking about two directions out of an infinite number. Right? You could be going up here, but then going down over here. You wouldn't really have a minimum. Yeah?
Can you just plug in points near that point into the equation?
Yeah, but then I can always argue, oh, there's just a point you just didn't plug in to try, and maybe it would have worked. How about looking at what this looks like?
What a novel idea.
What kind of surface is that?
That's going to be an ellipse, right? Yeah, it's going to be an ellipse.
No, that's a,
Oh, we're in
Yes,
3
yes,
dimensions. What?
Oh,
You need
no,
to-
it's, oh, duh.
Can't be an ellipsoid. Why not?
no Z.
The z isn't squared.
Right, it's going to be a paraboloid.
It's going to be a paraboloid, right? And it's actually going to be opening upwards, right?
Yes.
Which means if I find a critical point, it's got to be that one.
Yeah, there's no maximum. You can keep going
Right.
up. I see.
Right, and I know that that is the only possible place because anywhere else, the tangent plane would give me a direction that's not flat, right? Which means that my partial derivatives would not be 0, right? The only possible case is here if I'm at the bottom and the tangent plane is flat, like that, right? So just look at the picture. Right? Okay, let's move 1.
Yet another dull moment.
It's never a dull moment here. I mean, I'm entertained. Okay. 1 minus x squared plus y squared to the 1 squared. Okay. How do we find the critical points here?
Magic.
Not use magic on Tuesdays.
On Tuesdays.
Okay, so.
Negative 1, 2.
Huh? Negative
1 over 3.
1 over 3, yeah.
Into x squared plus y squared. Divided by 2 over 3.
Times to the negative 2 over 3, yeah.
2x.
Okay.
Same thing times 2y.
So this is actually minus 2x over 3 times the cube root of x squared plus y squared.
Did you square that as well?
Square what?
Next to the square root?
Yes.
Yeah. So the
Yeah,
whole,
because it's 2/3. So the third is the cube root and this 2 is the square root.
that just goes for the square root, right?
Yep.
Okay.
Okay, so critical points.
Zero.
And fx equals 0, fy equals 0, and this would have no solution. Why would it not have a solution? Because the denominator is 0 and both are 0 anyway, right? So, set fx, fy to be undefined, and then you find your critical points that way. You get 0, 0 as a critical point. Right, so in this case, the critical point didn't come from them being 0, it came from them being undefined. Just look out for that.
Do we have to mention that?
Come again?
Do we have to mention that?
Well, if you write 0, 0 came from this, then yes, I'd actually mark you've been correct. Because 0 is not a solution. Could you classify that one? Is this a maximum or a minimum point? 0, 0. Right. I mean, 0, 0 is not, the derivative is undefined there, but the original function clearly is, right? You can take the cube root of 0, that's fine. Would that give you a maximum or minimum point?
It would give you a maximum.
Maximum, why?
Because the thing with the x's and y's is being subtracted from 1.
Right. These guys are always positive.
Yeah.
And you have 1 minus a positive number, right? Since 1 minus this is always less than or equal to 1, because this is positive. And 1 occurs when x, y equals 0. All right, so there are some cases where you can just investigatively figure out, oh, this is a max or a min, right? By looking at what it looks like or some properties of the formula itself. Those are fine, but of course there are many other cases where this is either not possible or just not something you'd want to do. Because I mean, we know how to draw the easy surfaces I've told you about, but there are a lot of things where you're not going to know how to draw it. Let's face it. And then, how do you classify critical points in that scenario? Well, second derivative test, of course. That much is obvious. What is probably not obvious is how it actually looks, which by using the second derivative test in 3 dimensions. And what does that look like? Well, looks like the following. Function. X, Fy are continuous and Fx at A, B equals 0 and Fy at A, B equals 0 and define this word function, which we're going to call D, which is a function at the point A, B, given by the following. Fxx at A, B times Fyy at A, B minus Fxy at A, B, all squared. Then I'm not going to have enough space. We have several cases. One, if your D is actually greater than 0 and Fxx is also greater than 0, then f of AB is a minimum. This is greater than 0, and this is less than 0. F of AB is a maximum. If D is less than 0, then f of AB is a saddle point. Saddle point means it looks like a Pringle chip, right? So you're at the point where on one side it looks like a maximum because you're going down, but on the other side it's like a minimum because you're going up. Sort of like that x squared minus y squared thing. And 4, if D equals 0, test is inconclusive. And in that case, you try to use other investigative means like we did before. Right? But this is the second derivative test in calc203, right? So you sort of look at the second derivative where it's greater than 0 or equal to 0, right? So remember in calc1, greater than 0 would mean concave up like a cup. So you look like a minimum, right? Concave, less than 0 means concave down like a frown, maximum, right? You're down, you're feeling sad, you frown. Whatever mnemonic you want to apply to it, you can just remember that. But your d, this thing, how it's defined, has to be greater than 0. And the book uses fxx, but you can also check fyy. The formula, the theorem would actually hold with fyy as well. But that is called the second derivative test. So you compute this function d at some given point that you know is a critical point, and based on the outcome, you can tell is it a max or a min or neither, or I just don't know using this test. So with that, let's actually do something. Oh, how do we remember? Mnemonic. E is equal to, it's actually the x y, by that guy. Sort of the 2 by 2 determinant, where you remember you multiply this minus you multiply that. Right? This and that are equal because we know that these guys are continuous. So Claro's theorem tells us that it doesn't matter if you do the y first or the x first, they're the same. And so this happens here. But you can actually do that. So it's this times this minus this times that, and you get this one. And, I mean, if we're doing 11.8, this matrix would make more sense to you, but we're not, so I just don't want to go into it. But yeah, in general, this comes from what's called the Hessian matrix, and of course, in 4D, 5D, it actually is much different, right? You have a bigger matrix to take a determinant of, and the formula gets much more ugly. So we won't worry about that. It's sort of memorize at this point. We don't have the tools to understand the proof behind all of this in all its glory. So let's actually do some examples. Yeah, what does that look like? I don't know. I'm not going to like draw a picture and figure out the critical points on that. Is always bigger than 1, always smaller than 1? No. X, y equals squared y squared. Y equals x cubed minus 2y squared times 2y to the 4th plus 2x squared 1. Okay, so let's do the first one. A. So for these problems, I like to get all my derivatives out of the way at once. Like, that's just how I do it. So immediately I'm going to find fx, fxx, fy, fyy, and fxy. Right? I find it's easier when you know you're going to have to classify critical points at the same time. Just get all your derivatives out of the way all at once. Makes your life easier, I think. I find. So let's just get the derivatives out of the way. Fx looks like
Minus 3x plus 4y.
Fy
4x minus 4y.
Fxx.
Minus 6x.
Alright, so this means you take the partial derivative with respect to x, then x again. So I'm looking at this, differentiating with respect to x to get that. Fyy means take the partial with respect to y, then y again. So I'm differentiating this with respect to y. What is that?
4 minus 4. And they're both 0 for x and y.
And in this case, if I take this take this, differentiate with respect to y, I would get what?
4.
4. Notice that it's the same as taking this with respect to x, right? Whereas they're continuous here. So Clairaut's theorem tells you I could do either this with respect to x or that with respect to y, I'll get the same thing because they're continuous. Okay, so those are all my derivatives out the way. So now let's find the critical points. Right? And so this is sort of my system. It's always how I do it. So it's good to have like a system that you always do so you get used to it. So I get all my derivatives out the way, then I locate the critical points. Now to do that, what do I need?
Fx
You need this equal to 0. And this equal to 0. Okay. Now, so you have to solve a set of simultaneous equations. Now, in general here, I think, because it's not always linear, I find that solving for 0 and 1 and then plugging into the other and finding all the zeros that way is a good way to go. So from here we know that x actually equals to y. Substitute that into this one. And so let me actually do all these three things. This is 1, this is equation 2. From 2, x equals y, plug into 1, we get minus 3x squared plus 4x, because my x is equal to y, equal to 0. And so I can factor out the x, I get minus 3x plus 4 equal to 0. So my x is either 0 or my x is 4 over 3. Right? Which means the critical points are what?
0, 0, 4 thirds, 4 thirds.
0, 0, 4, 4 thirds, 4 thirds. Because my x is equal to y, right? So I have 2 critical points in this case. And now what I'm going to do is I'm going to do the second derivative test for each of them. So for 0, 0, you know that b is equal to fxx, fyy minus fxy squared. In this case, remember I'm at 0, 0, I'm evaluating these guys, right? So fxx at 0, 0 is just 0, right? So that's just 0 minus fxy is 4. So this is minus 4 squared, which is less than 0. This means the origin is a saddle point. Right? So that's that. I've classified the origin. You do the same for the other point. So here we have 4 thirds, 4 thirds. In this case, d is equal to fxx, fyy minus fxy squared. This is just a constant 4, so I know that's going to be minus 4 squared. Now, here if I plug in 4 thirds, yes. Here if I plug in 4 thirds, what do I get?
8 months.
Oh, wait, we're actually looking here. Here if I plug in 4/3, right, we're looking in the second derivative. You get what?
-8.
-8 by plugging in 4/3, yeah, -8 times -4, and that's actually positive, right?
Yep.
Right? Because this is 4 times 4, that's 8 times 4, so that's positive. And so now we can, there are two options that we could be now, right? And those options would depend on what?
The x-axis and the d, right?
Yeah. So since d greater than 0 and fxx is actually negative, so that's less than 0, this is a local, we're at the point, 4/3, comma 4/3 is a local, what is it?
Max.
Max. Right, second derivative less than 0 is a local max. Okay. Questions? So it's just a matter of finding all your partials, finding the critical points, and then you're plugging them into this function to see where you get the positives and negatives, and that will actually help you to answer the question.
Is there a name for the D to make it easier to remember or refer to? No, never mind.
Does it have a name?
Didn't mention
It's
it.
one of those generic names, discriminant or something. I don't
Okay.
remember. I don't remember the name. But you remember using that mnemonic thing, which some people find it easier with this. So, okay, can we do B? Can I get rid of this?
Yeah.
Now we're doing B. Right? So exactly the same setup. This is like my template for all these problems. What are all the derivatives? Fx? Fy? Fxx? Fyy? Fxy? Okay. Good. So now we want to find the critical points. We need this to be equal to 0. Call that equation 1. And this to be equal to 0. Call that equation 2. How do I solve these? We'll use 1, right? So here, this means that x squared equal to 0, or y squared, y equals 0, which means x equals 0, and y equals 0. And of course, if you plug them in here, that solves it. So here, we would have what? What do we have here? Is it just the origin? I mean, clearly here, if x equals 0, then your y should be equal to what? In this case. Right,
0.
you substitute one at a time. X equal to 0 here, what does your y have to be? It could be anything. Y could be anything. Right? Similarly, if y equals 0, then your x can be anything. In other words, our critical points, we have a lot of them here.
Huh.
So this means either all points in the x, no, just, okay. No, we only need the two, we only need the points. This means, X, yeah. And the origin is a special point I want us to look at. So mean, so check x0. Here your d would look like 0. I think the origin is the only one we have to check with. It would also be 0. I think the origin is the only place you have to check. Let's see.
So weird.
So this is a really weird problem, but I really wanted to focusing on the origin here because we can actually classify that. What is the origin in particular?
All z points on the x and y axis.
Come again? I mean, is it a maximum or a minimum?
It's a minimum,
Why would you say it's a minimum?
because it opens up on z. Is this in 2D or 3D?
We're in 3D. It's
Yeah.
z equals x or y squared.
Because anything squared that equals z is going to be a paraboloid of some sort. If you're doing x squared plus y squared equals z, it's going to open up.
So So once you actually move away from any of these planes, right, like you go into any region where both your x and y are positive or they're both negative, you get something that's bigger. I think there was something more about this. I forgot what I wanted to say about that example.
As long as it's not on the exam, we're okay with that.
It's a good example.
Because I think this one was the one with like a weird graph, like a feeling, but it's like.
Show him.
This is the graph.
So,
Here,
yeah, it was just crazy.
this is what,
Talk about it next time. Let's move on. What is the
it's weird.
C shouldn't be as weird. But yeah, this one's weird. Like every point along a plane is like a critical point. Right? So things can get really weird in calculus 3.
Thank you.
And just how weird is what. Okay, so we're actually doing C.
That's f of xy equals x cubed. I didn't know if you wanted to rewrite it. So that's 3x squared plus 6xy. And then that's negative 4y minus 8y cubed.
Is that right?
Plus 3x squared.
Oh,
This?
sorry,
Plus 3x.
plus 3x squared. Sorry.
Okay. And xx, differentiate this with respect to x.
6x plus 6y
Y, differentiate this with respect to y.
minus 4y squared.
Fxy, I can differentiate this with respect to y, for example. We need 3x squared plus 6xy to equal to 0, call this equation 1. And we need minus 4y minus 8y cubed plus 3x squared equal to 0, call this equation 2.
Could you divide that by 3 first?
I could divide by 3, sure. So this is x squared plus 2xy equals 0.
And then x times x plus 2y
X times x plus 2y
equals 0.
equals 0. So I have two options here. Either my x is 0 or my x is the minus of 2y, right? Now I go over here and I plug in each option. If x equal to 0, then I end up with minus 4y minus 8y cubed equal to 0, right? Which means I would have, I can take up minus 4, and this would give me 1 plus 2y squared, right?
Yeah.
And so what are the solutions there?
Line from zero.
Y equals 0 or
Plus or minus maybe 0.
No.
No.
Incomplete.
no real solution anyway, right? So y equals 0 is the only guy here, which means that this gives me the critical point 0, 0. There's no other solution. Now, if I let my x equals minus 2y, right? What would happen in that case? I would have minus 4, I'm probably going to need more space here. minus 4y minus 8y cubed. What was the other part?
Plus 2x squared, 3x squared.
Plus
equals-
3x squared.
Yes,
Plus 3x squared, right? Equal to 0. So I have minus 4y minus 8y cubed minus 2 squared is 4 times 3 is 12, y squared equal to 0.
Plus 12.
Plus 12. Right, so now I can take out y. And I would have minus 4 minus 8y,
yes.
8y squared.
You could take out the 4 as well. No.
Yeah, I could take out a 4, yeah. So I want to take out a minus 4 or a positive 4. Let's take out the minus 4. And so this would give us 1 plus 2y squared
Plus 3.
minus 3y. This is minus 4y, this is 2y squared minus 3y plus 1 equals 0. Does this have a solution? Doesn't? I can't factor? I put minus and minus? Yeah, that does it. So So this gives y equals 0, or y equals 1, or y equals a half, which corresponds to, since x is minus 2y, I would get x equal to 0, or x equals minus 2, or x equals minus 1, right? So all points are 0, 0, minus 2, 1, minus 1, half. For the origin, d would be fxx, fyy minus fxy squared. If I'm at the origin,
fxx is 6x plus 6y.
everyone's 0,
Um,
right?
Yeah,
So, how do you know if it's a max or a min? What's the original thing? There you go. No. Classify later when I get to the original thing. What if I plugged in minus 2, 1? fxx is what at minus 2, 1? Plug in minus 2 for x and 1 for y. What's the result? Huh?
minus 6.
And fyy?
36 minus 24.
Minus 28. And fxy? Is that 6y?
6x.
Okay, and the x is minus 2. So that's minus 12, and we square that. Is that greater than 0 or less than 0?
Less.
Hmm?
6 times 28.
Greater than 0. How do I know? 28 is 2 times what? Is it 2 times
14.
14, right? So this guy is actually 12 times 14. This guy's 12 times 12. And you can sort of factor it. You don't have to multiply 6 by 28. You just can sort of refactor things and you see. So this is greater than 0. Also fxx is, we already found it here, that's less than 0. At the point minus 1 comma a half. Minus 3.
Minus 10.
And this is
Minus 6.
32. Minus 6.
96.
Minus
so which is greater than 0, right? Because this is 30. This is
36.
30 minus 36.
That's 0.
this is less than 0. This is means what?
Saddle point, right?
Saddle point. Okay. Back to the origin. Said we come back to this. The original function was what? F equals
X cubed minus 2y squared minus 2y to the 4th plus 3x squared y.
okay. How do I know what the origin is? D gave me 0, so the test was inconclusive. How do I figure it out?
Oh, well, it's.
Here's a trick. Look in the plane. 0. Right, let's say I look in the XZ plane. And what is the function?
X cubed plus
Then I'd have Z equals X cubed, right? So in the XZ plane, the graph looks like this, right? So the intersection of this surface, whatever it looks like, when I pass through this plane, I get that picture. Can I tell at the origin, is this thing going to be a max or a min?
neither.
Neither. Is it a saddle point? Well, probably not. I mean, that's one of the things with this thing. It's like things can get really crazy.
So critical points are not necessarily max, mins, or saddle points.
No, you can have something altogether different. And one of the reasons why MATLAB is useful is you can plot that and try to figure out what the hell is happening in the origin of that guy.
What does the max and min actually mean? Like it's in a 3D graph, so there's no up and down.
No, it's like you're at the same thing. Like you're at the top of a hill, or except your hill now is 3-dimensional, right? Or you're at the depth of a valley. Right? If you're on a Pringle chip, you're at a saddle point. Right? Those are the 3 classifications we know, and there are actually a lot of other things that are going on. One, two, what is it? I'm actually not going to do the absolute maximum. I
Yeah.
think we'll save that for tomorrow. We'll stop there because I want to go slower. I don't want to rush through this in like 10 minutes.
Thank you.
It's 11:72 or?
No, because we didn't finish it.
Yes.
So you
You guys don't have homework.
Well,